positron, and then there is LHC. So when this was started, I think it was started in 1978. So the story goes back more than 100 years back, when the two big nations, the United States and USSR, they always had fight, and there is still today also, if you are following the news. So the competition was who will be leader in nuclear engineering. So nuclear engineering, the peaceful use was reactors, and the opposite of reactor is the atomic bombs. So, I mean, let's not discuss about the destructive part. Let's talk about the constructive, or the use of radiation for humankind. So, first of all, let's understand the thing that the accelerators are extremely diffused across the world. They can be of tiny sizes that we will see in the subsequent slices, and human-like size also. If you see on the left-hand side, there is some machine. This is a device for used in hospitals, and the patient goes inside it, and then the body is being scanned for certain things. So from few inches to meters to tens of kilometers, this is the size, and the cost which is involved is, let's say, if Indian currency, let's say 50-60 lakhs to several crores of rupees. So question, and and I said 78, so it took roughly 30 years for the Large Hadron Collider to commission. So question is, when it takes a huge amount of manpower and taxpayers' money, why should we put an effort to study them? Are there any use, or just the particle physics, or there is something else beyond it? Okay, so that is the motivation for this evening lecture, that why are we studying particle physics? Sorry, particle accelerators. So how many of you know, I mean, you must have seen in some movies, this is a Swift knife, and the way it is popular in the I mean, amongst the people is that it has multi-utility. You can use it for safety, for can opener, for drilling hole, and many things. So a particular device, and then it has many applications. So that's why it's a tool that is it is impossible to think that any technology, whether you talk of medicine or you talk of any semiconductor device, when you talk of any weapon, any type of sensor, where the particle radiation has not shown their presence. Okay, so particle accelerators can have in different sizes, can have different energies, and we will see that the particle radiation, so you have electrons, that is the negative charge particle, and then you have ions. Ions can be positive or negatively charged, and then depending on how do you ionize them. For example, if I take carbon, so if I strip one electron, I will have carbon C plus, and if I strip two electrons, a carbon plus plus, and at the most I can have carbon 6 plus, where I have stripped all the 6 electrons from its outer orbit. So basically what is there in one's mind is that particle accelerators, their applications are found only in the elementary particle physics. I mean, from LHC knowledge, you know that two particles, when they collide, they in a particular reaction, or in any reaction, they generate millions of subatomic particles, and they are being recorded. I mean, recorded as in they are detected by different devices. We call them particle detectors. And then we say this is the constituent or basic constituent beyond an atom. So 100 years back, I think in the 1900 something, 1902, 1905, it was said that it's only an atom, and then it has negatively charged, I mean, it has positively charged nucleus, and then surrounded by it, it has electrons, and then Bohr and many people gave their theories, some successful, some unsuccessful, in telling them what is inside the atom. But then, is it the only way? Is it the only reason why should we study particle accelerators for elementary particle physics, or at the time of the cosmology, which deals with the subject. It's a subject which deals with the Big Bang theory and other theories, which tells how the universe has been created. So is this the true? No. It will be clear in the next slide. So accelerators, which I mean, till this point of time, you have in your mind that it is used only in the discovery, like particle and nuclear physics. But then they have many, many applications, and that's how. So, I mean, this is a smart technique if you want a good amount of money from the funding agency. So let's say if you want to do specific nuclear physics experiments, if you say to the funding agency, give me this amount of money, and nobody will give you. So the smart way is you have to show some applications which are useful for the society. And in doing whatever you wanted, you will invariably developing a technology which will be useful for humankind, and that's how things go. So the useful technology is medicine. Nowadays, I hope that by the time you guys enter in your second year, it will be in the offline mode, and then you can see each other and teachers also and have good college life. But then COVID is the part which is which has created its bad impact or clear impact in everyone's mind, right from a KG student to the engineering student. So we don't have any medicine, but we have this vaccine shot. So you know how they are being built. How do I know that this particular combination will make a vaccine? So there also charged particle radiation has come into picture, especially the the vaccine which you had been administered. There is one accelerator facility in England that is, I mean, they have named it as Diamond. It is basically charged particle accelerator based light source, and using that light, the people have been able, the scientists have been able to get this vaccine. So other than that, you must have heard about a program called ITER, ITER. It's based in France, and the motivation is, I mean, when people were doing elementary nuclear physics experiments, so they came to know about fission and fusion. And when things are clear in one's mind, then they try to make it in the form of technology. So fission-based reactors, they are very old technology, and we have reactors across the world. India also have reactors. But then to have fusion-based reactors, uh, it needs uh, so what happens is that you bang the particle and you create a plasma, and then you have to confine the plasma for a certain amount of time, and then only it will have its useful applications. So there is no material in the world till this moment, that such a high dense plasma can be confined, because the temperature is more than the sun's temperature. So very, very strong superconducting wires have been created to create very, very high magnetic fields, and then you confine the plasma inside the magnetic field, and then you use very heavy ions, charge particle beams, to fuse to create the fusion. So that's why in ITER program also charge particle beams have left their impact. And then for the country like ours, where we have so much of pollution, so like you have dirty nalas, and then the sanitization is very poor in the rivers. So you need to clean them. So flue gas treatment. There are certain pockets in our country where you have, because of this dirt, enormous amount of this algae, and there are some natural sources of marsh gases where they have killed all the natural flora and fauna. So it has been found through theoretical chemistry studies that if you impact them, or if you treat them with several hundred kilowatts of electron beam power, then you can kill, or you can get rid of them, everything. And on the left-hand side, you can see the national security. So you can see, you can imagine it's a big this container, and then it's let's say it has having hundreds of mobiles and cars and some diamonds, vegetables, everything, and then in between somewhere you have put a small bomb. How is it going to help? I mean, how will one scan it? So on the right hand side, if you see on the bottom left, there is a device. It's an electron beam based radiation which falls on it, and it gives you a picture camera. So it can give very clear picture. If you go to any airport, they also have radiation, but then these radiations are X-ray based. But these are not good enough for ship cargoes. So there you need to have charge particle radiation based screening of the material. And then you have industrial applications. Let's say, I mean, you have been studying from your childhood that India is the agricultural country, and then it has a good revenue generated by sending spices and other things. So any nation will admit or will accept the food products only if they are radiation processed, because once you process them, then you increase the lifetime of the product. Similarly, in the hospital, the surgical instruments which you use, they need to be sterilized. So all these things are done by electron and ion beams. Next, in the industry, it comes the ion implantation. It's written. Now you talk of devices like, for example, a simple storage device, a pen drive. So in my times, when I was of your age, we had 1.4 MB floppies and few MB, I mean few MB pen drives. Now you have GBs and TBs. So how are the process? It's all done by ion implantation. So more details you will study if you have interest in a particular aspect in your subsequent semesters. But then this is the sketch that these are the applications of these accelerators. So this particular slide I have just shown that see 10,000 for semiconductor industry, that is ion implantation, then electron beam modification, irradiators, and such a tiny amount, 110 research facilities across the world. And this is 2008 and onwards. I think this is the slide I have taken, which was created around 2015 or 16. Still, this number is 30,000, the charge particle accelerator facilities across the world, and then it's peanut, which is being poured for nuclear and particle physics. So here the money goes, and from rest of them you generate money. So that's how the economy goes hand in hand. All right, so now when we talk of charge particle accelerators, it's obvious that you have a charge particle source, and then you give energy to them, and the energy is basically the kinetic energy. So all of you have studied at some point of time that you want to accelerate something, charge particles. So the strongest force, I mean, you know that you have gravitational force, you have electromagnetic force, and you have weak forces and strong forces. Amongst them, which has long range, is the electromagnetic force, and that's why you need charge, which is important. See, particle energy, I mean, giving kinetic energy to the particle is important, but then since the way you can create that high energy, I mean, can you think of any device where you can impart, let's say, 1 mega electron volt energy to a very small dust particle? Answer is no, you cannot do that. So that's the reason you need charge particles. And then there are certain things when we talk of SI units, but then when we talk of specific subject, so depending on, I mean, let's say somebody asks you, what is your height? Nobody will say, will answer that, oh, my height is these many angstroms. Nothing wrong, but then doesn't make sense. So similarly, when you talk of charge particle accelerators, nobody talks of joules or joules per kilogram, this type of units. So the most standard unit for energy is electron volt, and you know the relation between electron volt and the coulomb. They are related by this factor 1.6 10 to the power minus 19. So the units like keV, that is kilo electron volt, mega electron volt, giga electron volt, tera electron volt, these are used. Similarly, for the momentum, we don't use Newton meter. What is that? Kilogram meter per second. Nobody uses that. The standard unit in the context of particle beams and accelerators, the standard unit is EV by c, where c is the speed of light. And then you can have keV by c, meV by c, or gV by c, and things like that. All right. So let's say we start with the, let's say I want to study let's say somebody has given me a material and somebody wants to know, tell me something about it. So first thing comes to my mind is I would like to see how hard it is. And accordingly, I would like to have a source or any probing material which can break it. So if the characteristic, what we call it as the energy, let's say something is very soft. So if you touch it by fingers, you can say, okay, this, and then by applying little force, you can break it. Let's say then is you have a material which is relatively hard, so harder, and then you need more and more energy. So all of you have studied in your Jain preparation that there is something called de Broglie's wavelength, which basically gives me the concept of wave-particle duality. So if lambda is denoting the wavelength of that wave, associated wave of that particle, and the particle's character is being decided by the momentum of the momentum. So the two are related by this relation. De Broglie wavelength is h by p, where h is the Planck's constant, p is the particle momentum. So higher the energy of the particle, P, obviously the resolving power, or up to what extent you can break it, that will tell me what is the lambda. So higher the value of P, lower will be the value of lambda. So it's a simple question. Let's say I know all of you are aware about optical microscope, the microscope which you have used in your, I hope you have seen, if not used, in your 8th, 9th, 10th, 11th, 12th, at some elementary level in your schools. And then you have also heard about there is something called electron microscope. So without going into details, what is there in electron microscope and what is there in the optical microscope, the name suggests that in the optical microscope you have photons, and in the electron microscope you have electrons. So it's a homework, not homework, just do it using a calculator. That if I have an electron microscope and I am having a source of electrons which is producing 1 keV energy, then what will be the associated de Broglie wavelength? So that will come out to be a number. Smaller the value of wavelength, and that will tell me up to what extent I can see what is there in a microscope. So let's say lambda comes out to be 1 micron, so I can resolve whatever small organism or material I am seeing up to 1 micron level. If the energy is more, then lambda will be smaller, and then I will say, oh, now the lambda is, let's say it is now 100 nanometers. So I will say now I can resolve the organism or material up to 100 nanometer. So do this exercise just as a fun, and you can very well see that why electron microscope has better resolving power compared to same energy photon in an optical microscope. Okay, so using the same relation. Now, on the right-hand side, I will show you, we will discuss in subsequent lecture slides, that if you have a charged particle, just imagine a charged particle, and if it is going, let's say, in a straight line with the same kinetic energy, then nothing is happening. But then from your JE preparation and otherwise also, you know that anything which is moving in a non-linear fashion, it can be circle, it can be some curved path. So we say that there is always an acceleration. Even if the speed of the particle is not, if the speed of the particle is same, but then because of the direction is changing, we say that it is being accelerated. So there will be an radial acceleration, and that's what I am sure. So anything in the context of charged particle, if it is in the accelerated, it can be acceleration or deceleration, it starts emitting radiation. So in this picture on the right hand side, so this square-like boxes, these are the black boxes or structures which are some magnets and then some accelerating devices, which is moving in a circle round and round and round, almost at the speed of light. And then tangent to the beam path, the photons are coming. So these are the useful synchrotron, useful light, we call it as synchrotron. And we will discuss how this light is useful. So another simple exercise is for you to verify yourself or find something that if I have a charged particle electron whose momentum is 1 GeV by c, so what will be the de Broglie wavelength? So that will help you in finding that up to what level. So I mean, if it turns out to be less than 10 to the, I haven't calculated, but just giving you an idea. If it is less than 10 to the power minus 15 meter, which is typically the nucleus size, then I say that this momentum or this energy is not good enough to probe inside the nucleus. So if it is less than 10 to the power minus 15 meter, I will say this is the good enough energy that I can probe and I can see what is there inside the nucleus. So this is how things go. All right, so moving on. All right, this is the picture which was, you see, uh, how many, 5 and 20, 125, 27 years. This was the first light source. So it was Röntgen's X-ray tube. This is such a small device, you see. This you must have studied in your 12th, that you have inside this glass tube, you have high voltage separation between two, and then there is electron emission, and then you accelerate them with a very high potential difference created there between the two electrodes. And when these electrons, they hit at the window, so you can see there is some tip on the top. So you apply some magnetic field and then allow the charged particle, the accelerated beam, to hit on that material, so it generates radiation, and that radiation was used for as a light. And you can see, and this is 1895 picture. I can't read it, but that wherever it was done, so there is some maybe some lady, I guess, wearing a big ring, and you can see the bones and then the picture of that ring. So see, this was done so long when you don't have any Google computer or any artificial intelligence machine learning, so it's just the human brain. So this is really very tiny, maybe 2 or 3 feet. That's it. That's it. This entire tube. This was the first thing, and then the smaller versions were there, which you can see in the glass tube. So this was the historically the first thing, and then you have big devices. I'm sure all of you have studied at some point of time that Einstein said that there is an equivalence between mass and energy by this relation, E is equal to mc square. So if I want to create a subatomic particle, so you have to break the actual particle with which are moving in opposite direction. So you can have two type of experiments where, Rutherford-like experiment, where one thing is fixed, target is fixed, and then there is a beam which is colliding and hitting it and then breaking and smashing it into subatomic particles. But then at the center of mass, the energy will not be very large. And then you have Large Hadron Collider. You see that there is this blue one cylindrical. This is all cartoon diagram. This is a detector. And then from one end there is a particle, and then from the other end there is another particle. They come and they smash at very high energies. And at the center of mass, just note it down, I have not written, for very high energy accelerators. Let's say the particle beam, energetic charge particle beam, which is shown in blue, and the another charge particle beam, which is shown in magenta or pink, when they are coming at the energies of hundreds of GeV or so, at the center of mass, the energy will be double. Let's say the first particle beam is 100 GeV and other one is at 100 GeV. So once they collide, so at the center of mass frame, the energy available will be approximately double that. I mean, we are not doing that maths because that is at the advanced level. So just note it down. 200 GeV energy is available, and then it smashes, and then it gives rise to burst to several subatomic particles, which you detect them and then tell them this is my model or this is this thing. And this is just shown on the right, I mean in the middle side, there is a Large Hadron Collider. Somewhere it is written CMS, ALICE, and other things. So CMS is a specific detector. It is compact muon solenoid. ALICE, I don't know its full form. It is also some abbreviation of some detector. ATLAS and SPS, they are the abbreviations of certain small accelerators. So you never ever have the acceleration in one single go. So you start with keV, kilo electron volt energy, then you accelerate to 1 or 2 MeV, then you accelerate to 20ish or 30 MeV, then you go to 100 MeV, then you go to 1 GeV, then you go to hundreds of GeV, and then you go to TeV scale. This is how. So that's how you can see there are so many lines, reds and greens and magenta and blue. So these are, so at the end, the biggest one is LHC. Okay. And this is a cartoon diagram. It shows that in the ATLAS is also one of the detectors facility. This is a cartoon diagram that two energetic particle beams, they collide, and then they gave rise to Higgs boson. And this is just a picture that at a Higgs, whatever he predicted in early 60s, at that energy, there is indeed a signature that there something is happening. And this peak, in fact, confirmed the presence of Higgs boson. And this is the actual site on the left-hand side. This is the tunnel where the one particular accelerator section is shown. All right, so this particular slide, though I have already discussed, just to tell you the importance of the pi accelerators, that you can Google search it. Many international facilities, not in India, using charge particle accelerator-based lights. How have they been very, very useful for vaccine for this COVID? It's not only COVID, or most of the drugs, they are, I mean, one has to do the what you call it as biochemistry. It's all done by something. So chemists, they all synthesize things, but then the aid is given by physicists or the applied physicists or engineering physicists. To me, the applied physics and engineering physics, that is basically same. Another important thing which I would like to draw your attention is, let's say somebody wants to know what is wrong in one's body. For example, there is a tumor or any cancer. Please don't be afraid, but then I'm sure all of you are matured, so you should be aware. So it was thought that you should inject a radiation source inside the body, but you know, any radiation which is being inhaled by the body is dangerous. So now the biologists, doctors, what they have come that there should be such type of radiation isotope, radioisotope, whose half-life should be approximately half a day. 6 to 8 hours is good enough. But then whatever studies were done, there was none radioisotope which was naturally occurring, which could give rise to, which has this half a day lifetime. Then, as you know, people keep doing researches and research, and then when this fission reactor was commissioned and many things were discovered, so there is an element which is named as technetium, and its mass number is 99. It is not occurring in naturally, and it was found that it is having half-life little above than 6 hours. That is T half time is 6 hours. And then it is the most wonderful uh, tool for the doctors. I have been told by the doctors at AIMS Rishikesh, if this we can produce in India, thousands of such facilities, they will be in demand within our country itself. So since we cannot have a reactor in any hospital, so only way to get this is by using charged particle accelerators. Okay, so the idea is you have, I mean, just giving you an idea, you have you need a roughly 40 mega electron volt proton beam, and then it falls on an element which is known as molybdenum. Molybdenum gets excited, and when it comes to its ground state, so one of the daughter elements is technetium-99, and that you have to use it for drugs. And it's written in the slide that skeleton, heart, muscles, brain, thyroid, all these places where other techniques is very, I mean, cannot be employed. Okay, so that is the beauty of this machine. All right, so let's do some physics part. Enough of the philosophy and the preamble that why do we need this? All of you know charge particle. Uh, I'm sure all of you have studied that for a charged particle, if you compare the gravitational force and the electromagnetic force, the gravitational force is small, very small, I think 10 to the power minus 30 order small, so you just ignore it, throw it away. So charged particle beams, they can talk only by two things, E or B, electric field and magnetic field. And you also know that electric field is the only thing which can impart kinetic energy, and magnetic field, they can just change the direction. They can just guide the particle. They cannot impart any energy to the charged particle. So question which may come to one's mind is, if that is the case, then why should I need magnetic field? Why should I spend money to create specific type of magnetic fields? Or for that matter, why do we need magnetic fields? So answer is, let's say I want to steer my beam. I cannot have 27 kilometers in a straight line. And more so, when we talk of beam, so beam is a collection of particles. Higher the number of particles, more will be the current, more will be the current, more will be the beam power, and that is our aim, to have more and more power. So you also know that like charged particles, they are unfriendly to each other. There is always Coulomb-Coulomb repulsion. So that is the problem. So even if you say or you design an orbit, which you call it as ideal orbit or design orbit, you can, whatever you do, you can never have particles to follow that path. So there will be deviation, and this deviation is harmful because at the end they will hit the beam pipe and then they will be lost. So you always need to guide them. So question is, guidance can be done by electric field also. But then you think, let's say I have a 1 GeV beam. Imagine in your mind that you are driving a car which is moving at 1000 kilometers per hour. And then to deviate it, you need a very, very strong force. So electric field can also solve the purpose. But then magnetic field is useful because it is always supplemented by a factor of V. So let's say I need hundreds of newtons of force. So for deviation, or to put the charged particle back on the right track. So for example, 100 Newton force will require certain amount of electric field. But then because of the presence of V, the requirement on the amount of magnetic field will be low. You get my point? You can do the job of deviation, I mean, applying the force by electric field or magnetic field. But then if you compare the electric force QE and then QVB, so magnetic field is supplemented by a factor of velocity. And for energetic means this V is very, very close to speed of light. So the requirement on V is small. So with the small amount of magnetic field, you can generate that big force, which is good enough to steer the beam. So that's why magnetic field, though it is not imparting any energy to the charged particle beam, still has very importance. All right, let's go on. So the simplest scheme which comes to your mind is, let's say I have a battery. I have a battery, it has a higher potential and a lower potential. Usually say that plus and minus, or plus and ground. And then you have a parallel plate capacitor like arrangement. So you generate electrons by some mechanism and then you leave it in this thing and then it will give a push and then they will be accelerated. Yeah, this is simple thing. But then the amount of current or the electrons, for example, will be very less in number. So because of the Coulomb-Coulomb repulsion, once they come out of the anode, they will be going in some different direction, let's say here or here or here, which you don't want. So in order to have some focusing effect, what you do is you just give some curvature to the cathode, and these are all numerical codes, sophisticated codes written, and then this is, you see, these lines, these are the electric field lines, sorry, and this is how your beam particle comes out of the source. And these are some more sophisticated schemes of generating electron sources. So when we talk of sources, or so for electrons we call it as electron source, and for ions we call them as ion source. Sometimes we also call them as electron gun and ion injector. Okay, the terminology. Okay, this is all the age when Europeans and British and Americans, they did something for the useful applications of accelerators. So now the question arose that how much this battery can be. I mean, if you say if I apply 25 volts battery, so I will have 25 EV electrons. So, okay, that is also energy, but then typically any charged particle beam which is less than keV, we do not call them as an accelerator. So minimum thing is that it should be of the order of kilo electron volt. Then only that facility will be called as acceleration. So keV, and then if somebody wants to go higher and higher, then what is the thing? So this is the picture. You just think at the home. So there is an AC generator, which is shown in the AC, and then you have capacitors and then diodes connected to each other in the Z shape. So let's say I have a capacitor, then diode, then capacitor, and then diode and capacitor. So at the end of one node, let's say here, you started with V is equal to V naught, so maximum voltage was V, and at the end of one cycle you will have V naught here. No, not sorry, this is not the case. Here at the end of one cycle you will see 2 V naught has appeared here, and the end of another cycle 4 V naught has been generated. And in this way, cascading, multiplying, you can have high energy accelerators. So on the right hand side, these were the two scientists, British scientists, Cockcroft and Walton. They were able to generate 800 kilovolts, 800 kilovolts, and then you put a proton, so it will be 800 keV energy, and then 800 keV energy, if you throw it or bombard it over lithium atom, so it generates helium, and this is basically a typical example of fission, and that they earned Nobel Prize in 1951. So think about it. I am sure by the elementary knowledge of how capacitors and diodes work, you will be able to know how 2V naught at the end of one complete cycle of the AC generator. So one cycle 2V naught, the next cycle 4V naught, next cycle 6V naught, and then. So in this way, things started. Now, next thing, this is Venn diagram accelerator. All of you know, if I take a charged sphere, just a sphere, conducting sphere, and if I somehow insert some charge inside the sphere body, so the charge will come appear on the outer surface. That you know, that is very well known because it's a good conductor. So this is what is shown, and I'm sure you also know what is the capacitor of a sphere. And capacitor is a geometry dependent thing. I mean, if you are in your, I mean, if you have any doubt, please do not think that capacitor has anything to do with the charge or the potential difference. Capacitor is always defined as, let's say, if I have delta V potential, so what is the charge it has created or stored inside it? This is how capacitance is defined. So ratio is important rather than delta Q or delta V. So once you have conductor, spherical conductor, its capacitor is fixed, its capacitance is fixed. Now by some mechanism, you are, I mean, this basically rubbing the brush with some belt, you are creating charges, and then that belt is moving through conveyor, and this is how you are transferring the charge inside the conductor, and then this conductor, whatever charge is there on the belt, let's say here, it all gets transferred to here, and in this way you are changing delta Q. Okay, and since its capacitance is fixed, so obviously delta V has to increase. So this is how you generate potential difference between this thing and the ground. So here there is a huge high voltage generated just because by this fact, by this exercise. So this thing is known as Venn diagram accelerator. In India we have at two places. One is in TIFR and other is in New Delhi. The facility's name is IUAC, Inter University Accelerator Center. So the problem with the this thing is you cannot have, I mean, and they are very expensive and they are very large in size. Let's say 7 or 8 stories building, even if you have to produce 3 mega electron volt. So you cannot go on and on and on. So what happens is if you go beyond that, even the vacuum gets ionized. So we cannot go more than 2 or 3 mega electron volt. Then people tried with putting some inert gases, so that they wanted to push the this limit of breakdown. So it was found that these two gases, freon and sulfur hexafluorine, especially this one is most useful if you put it inside the this facility. You can push the breakdown voltage to 7 megavolts in 1933, and nowadays people have mastered, and then somewhere around 20 megavolts is the acceptable thing, is the safe operational thing. So in a typical Van de Graaff machine nowadays you can have 20 megavolts generation. Question is, if that is the thing, how will I get GeV or TeV things? So obviously you have to think of some different mechanism, something out of the box. And by the way, in this mechanism, these are all single shot. I mean, you generate the accelerator, you have generated the potential difference, you put the particle, and then in a single shot it will be accelerated. Here also, in Cockcroft-Walton also, and in Van de Graaff scheme also. But then if I have to go beyond 20 megavolt, then you have to think something out of the box. So here is the exercise or question to all of you. Let's say I have a battery, and then I have a vacuum tube because they need a vacuum, and then I have made a vacuum beam pipe like this, and by applying certain number of magnets, okay, these are all magnets, and you know the role of a pure dipole magnets, okay, I should write dipole magnets, is to circulate the charged particle beam in circle, or to move, to bend the particle in a circular motion, that you know from your 11th 12th knowledge. So let's say it is a 100-volt battery, it's a DC battery, and then I put a charged particle beam, let's say proton here. So proton, when it is here, it sees the potential difference of 100 volts and it gets acceleration. Let's say initially it was zero energy, zero kinetic energy, and the potential difference was this 100 volt, and then in first shot it gets 100 electron volt kinetic energy, and then when the particle comes out, it sees magnetic field, and then it goes round and round and round and round and round and comes back to here. So question to you is, again when it comes here, so it is ready to get another kick, and then there is a kick. So again in the second round it will see 100 EV kick. So next time its energy will be now 200 electron volt. So in that way, if I keep making them circulating for a large number of turns, let's say for a year or so, so I can accelerate the charge particle. If this is true, then why are we spending so much money? Why can't we do it that way? So can anybody tell me quickly what's wrong in this concept? What are we defying? Where the physics laws are being uh, flawed? Well, what's wrong in that? कहाँ पे गलत हो रही है फिजिक्स? Anybody?
Sir, we are using magnets for the particles to rotate, right?
Hmm. Hmm.
So sir, magnetic field is helping it to rotate, but how is it increasing the kinetic energy?
No, I'm not saying that magnets are doing. Let's say after it has made one complete circle, it has come back to the positive potential of the battery, and then before it enters, it will see the 100 volt potential difference, and then it will get another kick of 100 EV. So by the time it exits from the this part, so total energy, kinetic energy will be 100 plus 100. So in the second run, it will be circulating with 200 EV energy, and again it will come here, it will see a potential difference of 100 volt, and then it will be 300. So if I keep doing this exercise for, let's say, 1 year, so I should get a large amount of energy without doing anything. So there is something wrong, because this is not. So what is wrong here? That is my question. Hello?
Yeah, sir, I think
So
that
One of you. Quickly, my dears, we are wasting time, losing time.
sir, I think that after going through one circle, the magnetic field has to, curve its rotation so as to keep it inside the pipe. So after
Right.
some energy, the rotation that the magnetic field has to cause, it will go beyond that. It will not be able to do that, and the particle will go striking to the pipe.
Right. So, simple words. So, whatever energy it has gained here, kick, but then magnets are doing the job of guiding them. It will tell them go there, but then it won't go on its own. It has to spend some energy. So, whatever energy it has acquired in the kick by the battery, so in making one complete rotation, it has lost all that energy. So next time when it goes, so here it had all 100 EV kinetic energy and zero potential. Sorry, from highest positive terminal to negative terminal, it gained delta V is equal to 100 volt. That is, kinetic energy is 100 keV. So in this battery, inside the battery, the potential energy was 0 and kinetic energy was 100 keV. When it comes out the battery, there is no source of energy, so kinetic energy will remain 100 keV. But then whatever energy it has, it will be utilized in making this rotation. So whatever energy it has gained, it will be lost in making one complete circle, because the role of magnetic field is to guide them, not to give any energy. So the particle has to spend some energy. So whatever energy it has, it will be spent. So when it has made one complete circle and is almost at the entrance of the positive terminal, its kinetic energy is now 0. So this is so if you keep it like that, even forever, the energy will be only 100 electron volt. And also, this also comes from Maxwell's relation. Have you studied Maxwell's equations? I doubt.
Yes, sir. There are four equations, line integral.
So there is this thing,